Haoxiang is a postdoctoral researcher associate at the Center for Nonlinear Studies at Los Alamos National Laboratory. He graduated with a PhD from the Department of Industrial Engineering and Management Sciences at Northwestern University. His research focuses on the theory of optimization under uncertainty, specifically in stochastic programming and robust optimization. He's worked in applications in energy systems, supply chains, logistics, disaster relief, and sports analytics. Take it away, Haoxiang.
Thank you, Carlton. So my name is Haoxiang, and thank you for everybody to come. So today I'm going to present my work in the optimal power flow problem in a distribution network under a new novel stochasticity setting called N-1 disruptions. So this is joint work with my coworker here at Los Alamos, Harsha Nagarajan. So first we are going to look at what is a distribution network and some modeling features we are including in our model. We are going to introduce the concept of stochastic disruptions and how to model it, how to model the multiple stochastic disruption problem using a multi-stage stochastic program. To solve that multi-stage stochastic program, we propose a stochastic dual dynamic programming based algorithm to solve that. It's essentially a cutting plane algorithm to approximate value functions. And we are going to show the experiment results, how it is, how efficient it is computationally. And we are going to move on, conclude the presentation with the future direction. So we focus on the distribution network, which is at the end of this power system. So it gets the power delivered to the customers and usually has a tree topology. So we are interested in the decisions, the dispatch decision within multiple 15 minutes time periods. And what we use to model the power flow equations is the Lindy's flow formulation. It's because of the tree network topology, the Lindy's flow formulation is a good approximation and also has a convexity property here. So we also, so here for the generation in the distributed energy resources, we consider diesel generators. And we have the ramping up down limits in between the 50 minutes time period. And we also model the batteries located in some of the locations. For the batteries, we model the efficiency curves for the charging and discharging as a piecewise linear function. Since the piecewise linear function itself is non-convex, we convexify it using the area below the piecewise linear function. And we need to decide for the batteries, the power capacity at the very beginning of the time horizon. And also for the operations, we need to decide how much we generate from the diesel generators and how much charging and discharging we do for the batteries. So we consider the stochasticity here as a power system contingency. So contingency here means that we have some components that are done, and we model those contingencies as scenarios. Contingency, we assume that contingency can last tau time periods, and then during that, no other component can fail. And after that, the system will recover back to normal with all the components functional. And here, different from the previous literature, we assume that the contingency can happen at a random component at a random timing instead of like every single time period you have a possibility of contingency occurring. So here in this graph, we show that so there are two possibilities of contingency we show. So in this contingency, the generator at node 2 is down. And in this contingency, the line between node 2 and 3 fails. So to model that contingency using some mathematical term, we introduce the concept of stochastic disruption. So normally, in the stochastic programming problem, like this on the left, every single time period you see an uncertainty. But here, since we are modeling some event that is not going to happen every single time, but in a random time, we introduce a stochastic disruption here. And that disruption, since it can alter the topology of the network or like can knock down some of generators, it can significantly change the model. So we assume that after the model parameters or model setup are deterministic after the last disruption. So suppose I have a disruption here, then after that, and we assume that no disruption occurs anymore, then all the following decisions are determined by this disruption here. And we assume that there is known probability distribution for the interarrival time between two disruptions. So because we can formulate this using a scenario tree type of structure, we can model it as a multi-stage stochastic program. So the key here is to identify the value function. The value function means the future cost given the history or given the state space where we are at. So the state variable here is the generation, because we need to consider the ramping up and down limit for the next time period, and also battery inventory, because it will tell you how much energy you can have in the battery. And also at the very beginning of the time period, time horizon, we have the setup for the battery capacity. And then the disruption can occur at a random time based on where it occurs. For example, here, the disruption occur at time period 2. So we deviate from the nominal plan that we're going to take to carry out the recourse plan. So for the nominal plan here, or corresponding to the first stage, means that we are going to carry out this decision until we see the first disruption. Once we see the disruption, we are going to go into a recourse action, and then we're going to carry it out, that recourse action, until we see the next disruption. So based on that, every single stage now has a random length, but we can still model this using this value function. So here it means this value function f2 omega means that a disruption occur at time period 2 with the scenario omega, and at the current time period 2, it will take in the state space as the generation, the battery inventory, and what battery setup is. Okay, so since we talk about the first stage as a nominal plan, which assume no disruption, and we are going to carry out that plan, we define the cost function as the cost between the time, T1 and T2, that consists of the load mismatch cost. So we assume that we allow some load mismatch for the power flow balance, and thus that you can always achieve feasibility here. It's a quite important assumption for the multi-stage stochastic programming setting. And here, and then we also include the quadratic generation cost for the diesel generators. And what we optimize in the first stage is the setup cost for the battery and the expected cost for between the time 1 to t, and then the future cost of starting from 1 plus t. So here the expectation is towards the scenarios of disruption and when that disruption occurs. Okay, so the constraints we consider here includes the power flow equations, the power flow balance, which is represented in the Kirchhoff's current law. And we have a quadratic or second order conic constraints for the thermal limit for both the lines and batteries. So the batteries here, the discharge should be less than or equal to the capacity we set up at the beginning. And then we have the generator ramp up and down constraints. Battery efficiencies are modeled as a piecewise linear function because it's a convex set. So we can just use a bunch of linear constraints to model that. And then we have upper bound and lower bounds on the series of variables here. So for the later stages, the only thing that differs from the first stage is we need to model the recovery time t. So here we assume that within this recovery time, no other disruption is going to happen. So once you carry out this value function f2 omega, the next possible disruption time you can model is f5. So starting at time 5. And here, because we have the ramping up and down constraints and also the line thermal limit, but for those components that gets knocked out, we also need to mark those failed components so that their constraints are no longer tight, limiting anymore. So so those failed components, the constraints are going to be vacuous using some parameters. And then the last but not least, we need to make sure that the information we get for this value function is consistent with what we have with the past. So what this value function takes from the past is the generation of the diesel generator and the battery history, the battery inventory at that time point, and the battery capacity. So all those are solved, are based on the nominal plan. For example, for the first disruption, all those are given by the nominal plan and then passed on to the value function. So SDDP, stochastic dual dynamic programming, it's generally used to solve this type of multi-stage problem. And it has come up since 1991 to solve the Brazilian reservoir optimization problem. And the core of this algorithm is to generate cuts to approximate those value functions. Those value functions, we can only write them down in the iterative recursive way. So we don't know the closed form for them. So that's why we need to generate lower bounds, a lower approximation to give them, to tighten those approximation for the value functions. So it's divided into two parts. The forward pass is generate a bunch of feasible solutions. And based on those feasible solutions, the trial points, we can generate the cuts for those value functions. So here, because we have a convex recourse functions, so all those value functions, we can prove they are convex, we can generate Bender's cut to approximate them. So the difference from a traditional SDDP is here we don't know how many time periods are in each stage, and we can do a little bit more in the cut sharing. It does not have to be done at the time point where the uncertainty occurs. We can actually do a cut sharing more than that. I'm going to show that in the next few slides. Okay, so we take in IEEE 13 buses. We actually have larger test cases, but for presentation purposes, I'm just going to show this 13 bus case. And we assume that the inter-arrival time between two disruptions is actually a discretized exponential distribution. And we penalize the power mismatch by a very large number. So here we set up the diesel generators in the central location, and then we set up batteries in the leaf nodes. So for our SDDP algorithm, very interesting, a good property is it is computationally efficient for a very long time horizon. For example, like 96 time periods here, it can still converge within 100 iterations, and it solves the problem within like a couple of hours, which if you use that for like a day-to-day, before the day operation, you can solve it and then just utilize the entire policy without resolving it again. And we compare our SDDP algorithm with like a extensive formulation. Extensive formulation is known to be computationally poor, and for the just to show that we can see that the extensive formulation can go out of memory with a very small number of time periods here. and but the SDP algorithm is not affected by the number of. I mean, it will the solving running time will increase, but it is not significantly impacted as extensive formulation, because extensive formulation grows in size of exponential. And also, if we have more scenarios, where the extensive formulation can go out of the memory very easily. And we can, the next thing, we compare our stochastic policy generated by the SDDP algorithm with a deterministic policy. Deterministic here means that we don't consider the disruption, the possibility of disruption. So we solve the problem, assuming no disruption can occur. And then once the disruption occurs for some sample path, we resolve it again, still assuming no disruption occurs until they reach the end of time horizon. So we can see that the stochastic cost is significantly lower than the deterministic strategy, mainly because we utilize more battery capacity. We set up battery capacity and we utilize the battery capacity here for the stochastic policy. So that the setup battery can prevent the power load mismatch here in case that we have some components done. Okay, so some other operation.
Can you, you're over time at this point, so.
Sure. So basically, one sentence conclusion, we model the power distribution networks with a multi-stage stochastic program. We propose a SDDP decomposition method. We provide some operational insight. And for the future, we can include some more integer variables and include more uncertainties such as wind and solar generation. So, thank you.
Thank you very much, Haoxiang. You have one initial question in the Q&A, which is how does the tree in page 6 and 7 differ from a tree-like Markov chain?
So that's a very good question. So the Markov chain, it's kind of similar to, so if you consider that as a, if you consider all the possible scenarios as a node in the Markov chain, then it could be, it could move from one node to the other. So it's kind of like a policy graph in the sddp.jl, if you have seen that package. So each of the scenario or value function can be represented by a node. So that node can be kind of considered similar to a Markov chain node there. But Markov chain, usually we have like a time periods based on like for the transitions. So here we don't base our transitions on time periods, and it could take more than just one time period to do the transition. So that is, I guess, the difference between this and the Markov chain.
Great, thank you very much. Any other questions for Haoxiang? I'll ask one quick one. If you were going to postulate the limit of the scalability of the method to, you know, number, like how big the network, how long a time horizon, you know, rough guess, how big do you think it could go?
So we tested the biggest one we tested is 123 bus with 96 time periods. So it can solve that. I mean, we have to use the server, but it can solve that within like a couple of hours. The key question here is what's the dimension for this value function? Like how large is the dimension for the value for the variables taken in as a value function? So that is usually like 20 to 30, I would say.
Okay, great. There is one more question from Dan. Haoxiang, thanks for your talk. How crucial is it to have a linear power flow approximation? Would convex or even non-convex power flow models be acceptable here? What is the fundamental reason you need linearity? And
we actually solve
tractability question mark.
Yeah, we actually solve a convex recourse. So here we have the SOCP the SOCP constraint for the thermal limit. So those are modeled as SOCP constraint. So I will say, like, if we have other convex formulation, it will pretty much perform in the same like scale. That's actually something that we are going to test like right now. So to compare like different formulations for the convexification. But for the non-convex, that's the hard part, because for the non-convex recourse, we can't really use any cutting plane method to approximate, because I mean, cutting plane, you naturally assume that there is a convex structure so that you can generate a like valid lower approximation. So that is something that we want to look at in the future once you include like binary variables, or not even just like a non-convex power flow equations. That could be something very difficult.
Okay, thank you very much. We'll have to move on. If you have more questions, please put them in the chat. We'll get them, or the Q&A bar, and we'll get them answered.